Hello students, welcome to the class. So today we will see the NCERT chapter 6 equilibrium. So today will be the theory part 5 in which we will cover section 6.7. This is the disclaimer. Now in this class our objective would be to build a bridge between equilibrium and thermodynamics. We have already dealt with this thermodynamics thing. Now we are on the verge of completing the equilibrium. This both branches are very important to be reconnected, so that you can know the spontaneity as well as the amount of substance directly from one equation. So we will look onto that equation, and that equation will contain three things: equilibrium constant K, reaction quotient Q, and Gibbs energy G. Now talking about these two terms, which is equilibrium constant and reaction quotient, is dealt in the previous class. And about Gibbs energy change, so this is a part of thermodynamics. You can just watch our lectures on thermodynamics. There you will get the idea of Gibbs free energy. Although you don't know it, I have just put up a small definition. I will try to explain it in a simpler term, that what is Gibbs energy. So don't worry if you are not knowing about this thing. As I already mentioned, we are covering the 6.7 section. So its name is relationship between equilibrium constant K, reaction quotient Q, and Gibbs energy G. After covering this part, we will do some problems: 6.6, 6.10 and 6.11, which is of NCERT. Now these three questions are very important because it covers all the key concepts that you are going to see in this lecture. So let's start our discussion. So first of all, we will talk about the Gibbs energy. Now you can think of Gibbs energy as a thermodynamic potential. How you can correlate it? Suppose you are doing a work which requires 5 kilojoule of energy and you are having 10 kilojoule of energy. Then in that case, you will do the work easily. Consider a second case. You are having 2 kilojoule of energy and you have to do that same work which requires 5 kilojoule. Now in this case, you will not be able to do the work because you don't have enough energy. So this is a kind of energy which is stored in you, the potential energy which is stored in you. In case of the systems, thermodynamic systems, this energy is called as Gibbs energy, which is a kind of thermodynamic potential stored in the chemical species through which it does the work. And for a spontaneous process, its change should be always negative. Now why I am saying it? It's very simple. Suppose you have 10 kilojoule of energy and you have to use 5 out of it, then the final energy that you will be left with is 5. If you subtract final minus initial, you will get a negative value. Means the change will be always negative. Similar to that, if you want to do a chemical process which involves your thermodynamic systems, then in that case, your Gibbs energy must be following a change of negative. Okay? Is it clear? Now, if this is clear, we can now develop a relationship between this delta G, Q and K. We will talk about this K later on. First, we will see the relationship between delta G and Q. So it is written as delta G is equals to delta G naught plus RT ln Q. Now what are this delta G and delta G naught? So it's very simple. If G is the Gibbs free energy, then delta G is the Gibbs free energy change. So it is basically dealing with the change. So delta is representing here change. Now this thing is at non-standard condition. If you are taking standard condition, then in that case we will call this as delta G naught. Okay, standard free energy change. What are R and T? You know it very well. R is the gas constant. In terms of your SI unit, you take it as 8.314 joule per mole per Kelvin, and in terms of liter ATM per mole per Kelvin, you take it as 0.083. Right? Further, T is the temperature, which will be always in Kelvin for our calculation. Remember, this is very important in your numericals. Students often make mistake of not converting the degree Celsius temperature to Kelvin scale. So always try to change this scale. Okay, now here's a note for you. If you are trying to calculate the temperature change, suppose, then in that case, you are not liable to convert the temperature into Kelvin. Okay, so you can just calculate the change, just subtract the final minus initial. You don't have to worry about the scale in that case. So this is a very important point. Now, if I look at aspect of this reaction of this equation, which is at equilibrium. Now what will happen at equilibrium? You know it very well. After equilibrium, there is no net change in the reaction. Means the reaction has no further tendency to go on. Now, why is it happening? Because all the energy which was stored, the thermodynamic potential which was stored in the system is being lost, right? And now it has no further energy to bring out the next chemical reaction. As a result of it, you will not see a change in the Gibbs energy. And it's obvious because all the energy is being used up, so you will not see a further change in the Gibbs free energy change. If it is clear, then what will happen to the Q and K? Q, it will be converted to K. Now there may be cases, if you are considering in terms of concentration, your QC will be converted to KC. If you are considering the pressure, partial pressure, your QP will be converted to KP. So depending upon the case that is given, you can change your QC to QKC and QP to KP. Now let us substitute these two values of delta G and Q in our previous equation. So what was our previous equation? It was delta G is equals to delta G naught plus RT ln Q. If you substitute this, we will take delta G as 0, very clear, then delta G naught as it is and Q as K. So final equation will be, on rearranging we will get delta G naught is equals to minus RT ln K. Now this equation is very, very important. How? You can calculate Gibbs free energy change at standard condition if you know the equilibrium constant, and if you know the equilibrium constant, you are in position to tell the spontaneity of the reaction. And it's a wonderful thing because K is something which can be calculated easily. You know that after getting the equilibrium concentration, you can easily calculate the concentration. So that's a simple thing as compared to the Gibbs free energy change, which is a kind of thermodynamic part. You don't need any advanced technique for it, and that is the reason this equation is important. Because concentration is something we can calculate very easily. Can we simplify this equation further? Yeah. So ln can be written as 2.303 log. So we can write this thing as delta G naught is equals to minus 2.303 RT log K. So instead of ln, we have taken 2.303 log. Now this conversion is very, very important. Why? Because in some cases you will not get the value of ln x. Suppose your K is coming out as x, so you don't know the value of ln x, but in the question you have the value of log x. So what you will do, you will convert your ln x into log x by multiplying with a factor of 2.303, and then you can calculate your final answer. Now can we rearrange this equation further? We know that the equation is delta G naught is equals to minus RT ln K, but suppose the question asks you to calculate the value of K. How you will do it? Now here most of the students face difficulty because they don't know how to bring this ln on the opposite side. So it's very simple. Suppose first of all what we do, we keep all of the things except your ln on the right hand side, which is your delta G naught by minus RT by cross multiplying it. So this is the value of ln K. Now to bring this ln, we will simply take the anti-log or the exponential. On taking the exponential, what will happen? Ln K will be converted to K, and this whole thing, this delta G naught by minus RT will be going to the power of E. Now these are the two equations that are used frequently. Equation number 6.22 to calculate the Gibbs free energy change, and equation number 6.23 to calculate the equilibrium constant if you know the Gibbs free energy change. Is this part clear to you? So this is very, very important to understand how I derived this equation. Now let us look at the different aspects of this equation. We know that our equation is K is equals to e to the power minus delta G naught by RT. Now what will happen to the value of K if we change the value of delta G naught for different reactions? So let us deduce a table in the same form. So this is your table that you will get. So there are three cases here. First case, your delta G naught is less than 0. Second case, your delta G naught is greater than 0. And the third case, your delta G naught is equals to 0. Basically, we are putting it as negative, positive and 0. Now, you know already from thermodynamics that delta G naught is less than 0 means the system is doing a spontaneous work in the forward direction. Whereas in the case of positive value, for the Gibbs free energy change, you are doing a non-spontaneous work in the forward direction. And the third case is delta G naught means the system will be at equilibrium under standard conditions. So these are the three cases. But can we get an idea about this equilibrium constant? Yes, it's very easy. If you take this thing delta G naught as negative, that means this whole term on the power will go to positive. Why? Because delta G naught is multiplied with a negative sign. R and T are already always taken as positive because R is fixed and T is temperature, which is something we take it in positive terms. Because negative Kelvin temperature is not attainable. It's very difficult. And in questions, you will not see it also. Now, if you take the value of R as positive, T as positive, and delta G naught as negative, then this whole thing will become a negative part, and this negative multiplied by the negative sign will give you a power as positive. Now remember students, if you are taking a power of positive for anything, not only for E, you can take 10 to the power, you can take 2 to the power, and if you are taking a positive term in the power, then that whole calculation will give you a value greater than 1. Okay, it will always give you a value greater than 1. But if you take delta G naught greater than 0, then what will happen? Then this whole power term will become negative, and you will always get a value of K which is less than 1. Of course, that value will be greater than 0. It's not possible to keep it 0 because that is only possible if you are having a base as 0. So that is not acceptable. So you will only get a value which will be greater than 0 and less than 1 in case of delta G naught greater than 0. Now what can be implied on the spontaneity? If you see on the favored direction, you can see that K value is greater than 1 now. That means your product's concentration is more as compared to the reactant's concentration. That is the only way you can keep the K value as greater than 1, right? So you can also say that product is much more favored. And if product is much more favored, that means reaction is going more into the favor of forward direction. This is the only way you can get your more product formation. Similarly, if your reactant is favored, that means your reaction is much more approachable towards the backward direction. So it is non-spontaneous in the forward direction. Whereas in the third case, if you consider, you have delta G naught equals to 0. And if you put e to the power 0, it will give you 1. That means K is equals to 1. So both of the products and reactants are not favored in any way. They are equally approachable. Got it? Clear? So this is your thing. Now we will try to do a question on the same. Here is the equation given for you in which carbon dioxide is reacting with carbon to give you carbon monoxide, accurately 2 moles of carbon monoxide, and the Kc value is given as 3. Now if you are doing this whole reaction as 1000 Kelvin, and if you are keeping the pressure of carbon dioxide as 0.42 and pressure of CO as 0, then you have to calculate the equilibrium partial pressure of carbon monoxide and carbon dioxide. Remember, if the carbon monoxide is having an initial pressure of 0, that means no amount or no traces of carbon monoxide is present in the initial phase. Now I will give you some time to solve it. Just try it by yourself. Use the ICE table taught by me in the previous class, and you will easily find the answer. So you have 15 more seconds. Just use the ICE table. Take the change as X. So this will be a hint to you. So your time is up. Let's see how we'll solve it. Suppose, what are the things that are given? First write those things. So we are given with the value of Kp to 3.0. Then we are given with the initial pressure of carbon dioxide 0.48. There is no presence of carbon monoxide. So that is indicated by 0 partial pressure of carbon monoxide in the initial phase. Then further, if you write for the reaction, X as a decrease in pressure. So this is basically the amount of change that will occur upon the attainment of the equilibrium. Right, so we can represent the same situation in the ICE table. See, initially we have 0.48 initial pressure for carbon dioxide and 0 pressure for carbon monoxide. Here you can notice that we have not taken this carbon solid partial pressure contribution, and it's obvious because solids have no contribution to the pressure. After moving the reaction in the forward direction so that the equilibrium can be attained. Suppose X amount of change is seen in the pressure of the carbon dioxide. Now you can see from the equation that carbon dioxide has a coefficient of 1. That means minus X. So here 1 is multiplied with X, and it is not mentioned obviously because it will give you the same value. But there you will see a change in the carbon monoxide as it has a coefficient of 2. So if X amount of change is seen in the CO2, then 2X amount of increase will be seen in the case of carbon monoxide. And this is very obvious from the stoichiometric equation. So these are the concentrations that we will consider at the equilibrium pressure in terms of pressure, in the terms of bar, not concentration, in terms of pressure. So can we calculate the equilibrium constant now? So let us put this thing. Now our next thing is to calculate the equilibrium constant at in terms of pressure. So Kp can be written as, for the reaction, so this is your equation that we got, this is your table that we got. So Kp can be written as pressure of CO2 square times by the pressure of CO square times divided by the pressure of CO2. Now what is the pressure of CO? It is 2x, so we will take 2x square, and for the carbon dioxide the pressure is 0.48 minus x. So we put the same in the denominator. This whole thing can be equated with 3. It is given in the question. Then we have now one variable and we have one equation. We can solve it. But this equation is a quadratic type because x has a power of 2. So we need to use the formula to find the value of x. How can we do it? It's very simple. Suppose we are finding the possible roots of the previous quadratic equation. So this is your previous quadratic equation. I've just rearranged it. So 4x square plus 3x minus 1.44. Here a, b and c are the coefficient of x square, x and the constant, right, respectively. So a will be 4, b will be 3 and c will be minus 1.44. What is the formula to solve it? So x can be calculated as minus b plus minus root under b square minus 4ac. The whole thing is divided by 2a. So what is b here? It is 3. Instead of b square you can take 3 square. Then 4ac we are taking it as 4 multiplied by 4 and multiplied by c, which is minus 1.44. In between we will take 2 signs. So basically we will get 2 roots of the x because it's a quadratic equation and it is obvious. And in the first root we will take the positive part. In second root we will take the negative part. Then in the denominator we will take 2a, which is 2 into 4. Let's solve it further. If you solve this, you will get it as minus 3 plus minus 5.66 by 8. Now we will select the possible roots out of these two forms. So you will take the positive form only. Why? Suppose you would take the negative form, then what will happen? You will get a negative value of x, and that is not possible because you cannot change it in a negative way because the reaction is going further, right? It cannot go into the backward way. It's not possible because we have no carbon monoxide in the mixture. For backward reaction you need the carbon monoxide. So this case is obviously not possible. Therefore we will take the only positive part, and in this case you will get an x value as 0.33. Got it? Is it clear? So why we are neglecting the x negative part? Because there is no product present for the backward reaction, as carbon monoxide is having a 0 bar pressure. So we will further calculate the required thing because now you have only calculated this change. If you look at this table, you will easily find that how you will calculate the partial pressure of CO2 at equilibrium and CO. You just have to put this value of x in these two forms. So let's do this. So for partial pressure of CO, we will take 2x, which is 2 into 0.33. So 0.66 will be your final pressure of CO. Similarly, for pressure of CO2, you have to put x as 0.33 and 0.48 minus 0.33 will give you 0.15. So you can say that the partial pressure of carbon monoxide is 0.66 bar and the partial pressure of carbon dioxide is 0.15 bar. So this is your final answer. Let's move on to the second question. So for this question, the value of delta G naught for phosphorylation of glucose in glycolysis is 13.8 kJ per mole. You have to calculate the Kc value. Remember, you have to do a unit conversion here because R value is taken as joule per mole per Kelvin. So you have to convert this kilojoule into joule. Now, in this question, you have to use today's concept of delta G naught and RT ln K equation. Remember that equation? It's very simple. So I am giving you a hint in this way. Your time starts now. It's very simple. Just put the values and you will get your answer. Okay. So your time is up. Let's see what is the correct answer. How you will solve it? You are given with the value of delta G naught minus 13.8 kilojoule per mole, or you can convert this thing. I have told you to convert this. So on converting this kilojoule into joule, you will get it as 13.8 multiplied by 10 to the power joule, 10 to the power 3 joule per mole. Then what about R? R will be 8.314 joule per mole per Kelvin, and temperature is mentioned as 298 Kelvin. So to calculate Kc, we'll use the equation delta G naught is equals to minus RT ln K. Now in terms of concentration, we'll take K as Kc. So ln Kc will be now delta G naught by RT with a negative sign. If you put the values, so 13.8 multiplied by 10 to the power 3 joule per mole divided by 8.314 joule per mole per Kelvin multiplied by 298 Kelvin. Again with a negative sign. Remember, I have told you if you want to find the value of Kc, you have to take the E value. Okay, you have to take the exponential value. So let's do this. So upon solving this, you got ln Kc equals to minus 5.569. Then further we will take exponential to cancel out this ln. So Kc can be written as e to the power minus 5.569. Just use a calculator in this case. Now don't worry, you will get the value of e to the power minus 5.569 in the exam. You don't have to worry about it. If you do this calculation, you will get it as 3.81 into 10 to the power minus 3. You can easily see that in this reaction, you have a delta G naught value as what? You have taken this as positive. Therefore, you got a Kc value which is less than 1. See, it is 3.81 into 10 to the power minus 3. So this value is greater than 0 but less than 1. Now you can easily say that why a delta G naught value having a positive value is favoring the reactants rather than the product, because the Kc value is predicting the same. So the reaction will be non-spontaneous and will be more favored by the reactant. Moving on to the next question. Hydrolysis of sucrose gives us sucrose plus H2O. So hydrolysis is basically the reaction with water. As simple as that. So upon hydrolysis of sucrose, you will get glucose and fructose. So you are given with the value of Kc, which is 2 into 10 to the power 13 at 300 Kelvin. You have to calculate the delta G naught value at the same temperature. Your time starts now. It's very simple. Similar to the previous question, you have to solve it for delta G naught. You don't have to worry about the ln thing also in this case. You have 15 more seconds. So it's very simple. Okay, let's see the answer. Now, what else is given in the question? We are given with the value of equilibrium constant, which is 2 into 10 to the power 13 Kc. Then further, our gas constant we already know, it is 8.314 joule per mole per Kelvin. Then temperature will be taken as 300 Kelvin, mentioned in the question. You have to calculate the delta G naught. Now the equation that we know is delta G naught is equals to minus RT ln K, which is equation number 6.22. Further, we will take K as Kc because here we have to calculate the equilibrium constant in terms of concentration. So the final equation can be delta G naught is equals to minus 8.314 joule per mole per Kelvin multiplied with the temperature, which is 300 Kelvin, then ln 2 into 10 to the power 13. If you calculate this thing, you will get your final answer as minus 7.64 into 10 to the power 4 joule per mole. Now you can conclude here that the opposite thing is also true. How? We have taken a Kc value which is greater than 1. As a result, we are getting a Gibbs free energy change value as negative. That means if your product is favored, so the reaction will be spontaneous. So it is very clear from the value. So this was all from the theory part. Let's summarize this whole discussion. Now we are introduced with an equation which is very important, which says that if you want to calculate the Gibbs energy change, then you can calculate this thing in terms of reaction quotient, given that you know the value of delta G naught. That equation is delta G is equals to delta G naught plus RT ln Q. I would suggest you to remember this parent equation. It is very, very important. Now, if you take this parent equation at equilibrium, then in that case, your delta G becomes 0, K becomes Kc, Q becomes Kc or Kp, depending upon the situation. Then, what about the equation? The equation becomes delta G naught is equals to minus RT ln K. So K can be Kc or Kp both. So this thing is true only at equilibrium state. So this is all for today's class. I hope you enjoyed the session. Thank you.